This is the Step 3 video, Run Trial Models to Achieve CSE Targets. Let's go ahead and open up Streamline to begin. Okay, from our last video, we know we want to run a model to target 434% circulating load ratio and 37.7% bypass fraction. Recall from Module 8 that in order to change the circulating load ratio, we need to change the cut size, or D50C, of the cyclones. Also note, significant changes to the bypass of fines, such as when you alter the water balance around the cyclones, will affect the circulating load ratio. This makes sense, right? If the cyclone is sending fewer fines to the underflow, then the circulating load drops. Now, if circulating load drops, CSE drops. So what is the new equilibrium condition? It's tricky, right? Well, this is where Streamline shines. The program calculates the new equilibrium condition and allows you to adjust D50C as needed to hit your circulating load target at your specified fines bypass percentage. Let's go through an example. We'll click on Trial Models. This is a summary sheet where you can track the key parameters for each one of your model trials. For this demo, let's start by finding out what cyclone cut size, or D50C, we will need to hit our target of 434% circulating load ratio with a bypass fraction of 37.7%. To keep things simple, let's assume we're going to take any improvement in CSE as a reduction in ball mill power draw and steel consumption by reducing the charge level. This allows us to keep the feed tonnage the same as the survey case. Okay, so for our first scenario, let's type in reduced energy scenario. You see that the model state says initiate, and there are no values for any of the key model output parameters here to the right. These values will automatically fill in once we run the model. Lower down, we can see the comparison table. Clicking on the drop-down box, we can select which scenario to compare to the survey values. We'll come back to this after running a scenario. Okay, let's go to scenario 1 to start. Scroll up to the top and click here on the left, scenario 1, to navigate. At the top left of the scenario sheet is a box called Cyclone Model Shift Parameters. I'll cover this in more detail when we start the model run. For now, let's get familiar with the overall scenario page. To the right, you see a table of values and a corresponding graphical plot of the cyclone model. Right now, the scenario model is simply the survey cyclone recovery to underflow values. In the plots, both survey and scenario model values are shown with the survey values in black and model values in red. Corrected cyclone curves are shown below the cyclone model shift parameter box. Scrolling down, we see another graphical plot. This is the size distribution plot for the selected survey stream, and once we run the modeled size stream distributions will also be plotted. To the right of the size distribution plot, we see the model output size distributions in tabular form. They're not filled in yet because we haven't run the model. Below the table of size distributions, you can also see the modeled dry tons per hour and then the actual values from the survey, just as a comparison for a reference for comparison. At the very bottom of the page, we see a box labeled Model Controls. Here we can select which stream to plot from the drop-down menu. Right now it's on cyclone underflow. We can switch to cyclone overflow. I'll scroll back up here so you can see it. There, you can see the survey cyclone overflow values. I'll change that to the ball mill discharge. You can see that the title of the plot updates and the data updates as well. So again, this is the black dots, that's from the survey. Once we run the model, red dots will show up showing the comparison of the this model to the survey. Also in the model control box, we can alternate between the initiate and run states of the model, again using a drop-down box. An important note, when you make major changes to a model input, say the feed tonnage or power, or perhaps cyclone parameters, it's best to go through a cycle of initiate, then run. This allows the model to find equilibrium from a fresh starting point. If the change is small, the model will probably find the new equilibrium starting from the last equilibrium achieved. However, if the change to the input is big, the model may not reach equilibrium starting from the old equilibrium state. So if your model isn't coming to an equilibrium or something looks wrong, try cycling between initiate and run to see if that clears things up. Okay, the last part of the scenario page to look at is the key circuit parameters box. Here you can see a list of model outputs and how they compare to the survey values. There are two white input boxes here, mill power and circuit feed rate. Let's enter in the mill power and circuit feed rate now. We'll put the same thing as the survey values. 955 kilowatts, 126.6 tons per hour circuit new feed. Now let's scroll back to the top and have a look at the cyclone model shift parameters box. First, let's talk about what shift curve means. Remember, we need to change the D50C of the cyclone to change the circulating load ratio. The way Streamline changes the D50C is to shift the entire cyclone recovery curve left or right. Historically, this was a manual, graphical process we would do on a piece of transparency by plotting the points just as you learned in Module 7, then copying them onto the transparency, then physically moving the transparency left or right. Then we would read off the recovery values at each sieve size. You can imagine how painstaking this process originally was. Fortunately, Streamline does this for us mathematically by translating the points. Shift curve is how we control the process of moving the cyclone curve. A value of 1000, which has already been entered in, means no shift from the survey curve. The value 1000 is arbitrary and is used as a relative value. It has no physical meaning. Entering a larger value into shift curve moves the curve to the right, which will increase the D50C and reduce the circulating load ratio. Let's go ahead and play with shift curve a little bit here so you can see what I mean. First, we have to enter in the bypass value, 52%. We'll talk about it a little bit later, but what you can see now is that the red cyclone model matches the survey cyclone curve. Shift curve is at 1000. Let's put shift curve to 1200 and watch what happens. We can see that the red model curve is shifted right. You can also see that the model D50C has increased to 125 microns. The survey D50C was 90. Now let's try 800. The curve shifts left, and the D50C of the model drops down to 56 microns. Again, the survey D50C is 90. Let's set it back to 1000 on shift curve for now, so we can move on to the other controls. The next cyclone model control is called rotate curve. This tool is how Streamline can change the sharpness of separation of the cyclone as measured by the selectivity index. Selectivity index is covered in Module 7 if you need a review, but essentially it's a ratio of the D25C over the D75C. And remember, the subset or the subscript C refers to the corrected curves down below. So it'd be the D25 divided by the D75C. Larger SI values mean a sharper or more precise separation. Lower values mean a flatter or less precise separation curve. This time, 100 is the base value of rotate curve. This means the selectivity index will be the same as it was during the survey. You can see this here to the right. The survey selectivity index is 0.268, and right now the model selectivity index is 0.268 because rotate curve is set to 100. Just like shift curve, the 100 is an arbitrary relative value Streamline uses to rotate the curve. It has no physical meaning. If you set rotate curve to a value higher than 100, SI increases. If you set rotate curve to a lower value than 100, SI decreases. Let's set it to 120. Now you can see the red curve is slightly closer to vertical as the curve is rotated about the center point, the D50C. We can also see that the selectivity index has increased from the survey value of 0.268 to the value of 0.350 for the red model curve. If we set rotate curve to 80, we see the red curve flatten out. SI decreases down to 0.173. I recommend using caution with the rotate curve function. It's shown in the literature that modern, high-efficiency cyclones can provide a sharper separation, but sometimes it's difficult to gauge how much better. Additionally, there are literature references to increases in SI using more dilute cyclone feed conditions. You'll need to use good engineering judgment and consult with your equipment suppliers for guidance on how much to change the selectivity index in these models. For now, let's set rotate curve back to the base value of 100. Below rotate curve, we see adjust bypass. Recall from our CSE improvement target that we want this value to be 37.7. This can be entered directly here. Immediately, you can see the red curve drop down at the fine end. The adjust bypass value is a direct entry value. The value you enter will be the bypass in the model. Finally, at the bottom of Cyclone Model Shift Parameters, you see a selection box titled Cyclone Model. The choices are calculated or manual. If you remember earlier, I mentioned that we used to graphically manipulate the cyclone curves on paper with the transparency. Well, when you select manual, you see the yellow highlighted boxes in the cyclone model table switch over. I'll cycle through again so you can see. Calculated. Now using this set of values. And manual. These get crossed out and these get highlighted, the manual values. If you want to manually enter or refine the cyclone curve directly, this is how you do it. The streamline, shift curve, and rotate curve tools are handy, but at the end of the day, it is up to the modeler to decide if the cyclone model is appropriate or not. By giving you the option to manually enter the classification curve, Streamline allows you full flexibility to run the scenario you desire. Want to see what a perfect separation curve looks like? Go ahead and enter it in. But remember, models are just math. We need to make sure that what we model can be realized in practice. Let's switch back to the calculated cyclone model. Okay, now we're ready to run our first model. With shift curve at 1000, rotate curve at 100, adjust bypass at 37.7, and the cyclone model back to calculated, let's scroll down to the bottom of the page. There we are. We already entered a feed tonnage of 126.6 tons per hour. This is dry tons per hour entering into the circuit, the same as the survey. Mill power is set to 955 kilowatts at the pinion. Again, same as the survey. Now, let's switch model state from initiate to run. Once the model is finished calculating, we can take a look around. First, in our key circuit parameters, we see that cyclone bypass has dropped from 52% in the survey to our target value of 37.7%. D50C is still 90 microns because we didn't adjust shift curve from the base value of 1000. Circulating load is dropped from 434% in the survey down to 310% in this new trial model. Not surprising, considering we didn't change our D50C. But we did reduce the amount of fines reporting the underflow by changing the bypass. We didn't adjust rotate curve, so selectivity index stays the same at 0.268. Cyclone overflow P80 has gotten just so slightly finer, going from 126 down to 123 microns in this model. Why did it get finer? Well, look at the CSE down below. By reducing the bypass fraction, CSE at the P80 increased from about 60.4% up to about 61%. Let's scroll up and have a look at the model size distributions. Let's switch to cyclone overflow for stream plotted. And you can see the model and the survey data are close to the same. We didn't expect much difference because the P80 didn't change very much. Now let's switch to cyclone underflow. Here we can see the effect of reducing the bypass fraction. The model data in red is coarser than the survey data. If you're more of a table person, all the size distributions are shown in the table to the right of the plot. Additionally, you can see the effect of the change in the bypass fraction has made on the stream flows when you compare the modeled tons per hour to the survey tons per hour. Looking at the cyclone underflow, we saw the circulating load ratio dropped, and as we expect, the model tons per hour through the mill is much lower than the survey. Going back to the plot, let's have a look at the ball mill discharge. Here we see the red dots in the model are slightly higher than the black circles of the survey. This makes sense. Even though we made the mill feed coarser by reducing the bypass fraction, the lower circulating load ratio has allowed the mill to overgrind the material. This is why reducing the bypass only made a small change to the CSE. To get our circulating load back up to our target of 434%, and to avoid this overgrinding situation, we need to make a change to the cyclone D50C. So let's scroll up and do it. So, we want to increase the circulating load. This means we have to get a finer D50C by shifting the curve to the left. Remember, when using shift curve, smaller numbers move the curve left. Let's try 900. Since the model is still in run mode, as soon as we enter our 900 value for the shift curve, the model recalculates. We see that the curve has shifted left, and the new D50C, is 71 microns. We also see that selectivity index has dropped a bit. Let's tweak rotate curve to get back to the survey value of 0.268. Value 105 should be close. There we are. Now let's scroll down and see the effect of shifting our D50C from 90 to 71 microns on the circulating load ratio. Okay, so our CSE is better, so we're going in the right direction, but our circulating load is still only 335%. But wait, look at the COF P80. It's dropped down to 118 microns from 126. Let's go ahead and drop the mill power a bit, since that's the real goal of our scenario. If you remember, we want to take advantage of CSE by reducing power. Let's go ahead and back it down a bit to avoid overgrinding in the overall circuit. Let's try 900 kilowatts. We enter 900, hit enter, and there we are. Now the cyclone overflow P80 is much closer to the survey at 125. But our circulating load, well, it did come up a little bit because we reduced the power in the mill, so our per pass grinding went down. We're still not on target, so we need to go back up to the top and change the D50 a bit finer still. Let's drop shift curve down to 800 this time. And let's tweak rotate curve just a little bit to get the selectivity index back on target. Let's try 106.5. Okay. So now at 800 for shift curve, our D50C is 56 microns, and our selectivity index is back very close to the survey value. Let's go ahead and take a look down at the bottom and see what effect that's had on our modeled circuit. Okay, we can see circulating load is increased to 397%. We're getting closer to target, but not quite there. Cyclone overflow P80 has dropped down, so it's a little bit finer. Again, our CSE is getting better. Let's go ahead and drop our mill power just a bit more to try to get that COF P80 back on target. Let's try 850 kilowatts. Wait for the change to happen, and there we are. We're pretty close, a little coarse, but 128 microns versus the survey 126. But you notice by reducing the power, our circulating load went up again. Now we're getting close, 420% versus 434, which was our target and our survey value. Let's scroll back up to the top. I'm going to make a rotate curve change based on the fact that we adjusted the cyclone overflow percent solids target. If you recall, we checked earlier that the downstream operation could handle 40% solids in the cyclone overflow instead of the 51.5% solids that we had during the survey. Based on some literature research, I believe we can increase the selectivity index by about 10% due to the improved cyclone separation performance with a lower feed density. So let's go ahead and increase rotate curve up to 112. And you can see selectivity index increases here to 0.296. That's about 10% more than the 0.268 value that we measured during the survey. Let's go ahead and have a look down below and see where that leaves us in terms of the circuit equilibrium. Okay, we now see that the circulating load ratio is about 430%. This is very close to our target. Our cyclone overflow P80 is right on target at 126. CSE at the P80 is now just about 68%. This is 8% higher than our original survey value on an absolute value basis, or about 13% higher relative to the survey. The grinding circuit is now able to make target P80 of 126 microns, but the power draw of the ball mill is 850 instead of the 955 we started with. Let's call this close enough for our first trial model. Now that we have targeted the new improved CSE circuit with our model, let's make note of our D50C and selectivity index. 56 microns for the D50C and 0.296 for the selectivity index. And let's go back to the trial model sheet, clicking up here, and let's add that to the scenario description. Reduced energy scenario. D50C was 56 microns and SI was 0.296. We can see that right here. Enter. Okay, now that scenario 1 is in the run state, you can see that the key model parameters from the scenario have populated underneath the scenario description here. If we scroll down, we can actually make the comparison directly to the survey data using the comparison table. Scenario 1's already been selected from the drop-down menu, and survey is always the top. These buttons are nice. You can always click here, go back to survey, and there's your survey flow sheet. Click here, and that should bring you right back to trial model summary sheet. Okay, scrolling down to the bottom, here we can see the scenario description. This is the baseline circuit survey data used to create the mill model and initial classifier model. Both are in the run state, so that means the data has been populated across here. CSE at the P80, so we're at 60.36 at the P80 for the survey, and then this is scenario 1, reduced energy scenario with our notation written in from above. We've got run, all the data is populated. We've gone from 60.36 to 67.69, a difference, absolute difference of 7.33, and a relative difference of 12.15 change percentage. 75 micron was the CSE size of interest in this plant, so doing the same CSE calculations at 75 microns instead of the 126 P80 gives you 73 to 81% in terms of the absolute change, 7.9% in CSE at 75 microns and 10.73 relative change. Remember, we had 955 kilowatts for mill power in the survey. We took advantage of this improved CSE to drop the mill power down to get the same tonnage, and P80 down to 850, meaning we're saving 105 kilowatts running the circuit this way, which is an 11% change, or an 11% improvement or reduction in power draw. Same P80. These changes here are just due to whatever values numerically are past the decimal point, but essentially there's no change in a P80. We did give ourselves a little bit of a selectivity index improvement in this model, and again that was justified based on using a sharper separation, or it is a sharper separation. It was based on using more water at the cyclones. We also would have the choice later on when we actually size and select these cyclones. We'll choose high efficiency cyclones as well. So even though it's a 10% improvement, it's probably conservative in this case. Bypass fraction was another big part of the CSE improvement we went after. Remember, we had 52% bypass of fines in the cyclone underflow going into the mill. In this scenario, we've redesigned the water balance such that only 37.7% fines are bypassing the cyclone back to the mill. That's where a lot of a majority of the CSE gain is coming from. Again, because we didn't change the circulating load appreciably, we targeted the same here. In another scenario, you might want to actually look and say, do I have enough pump energy? I could probably even increase that circulating load further to get more CSE gain. And then finally in this column you can see circuit new feed, 127, 127. It was 126.6 I think. But essentially we're feeding the same tons, we're hitting the same P80, we're doing it with 105 less kilowatts, or 11% less kilowatts, and we're gaining that because we've improved CSE. The CSE improvement is what allowed us to make that improvement to the circuit. So for those of you who went through Metcom modules before the release of Streamline, you recall that in Module 18, Evaluation of Circuit Classification, that allowed you to estimate the benefits of improving CSE. But now with Streamline, you can see we can precisely predict the improvement in CSE. We can precisely predict the change in the tonnage, the grind, or the energy efficiency for this specific circuit, rather than having to rely on the rules of thumb that are in Module 18. For example, Module 18 doesn't provide a way to estimate the benefit of improved classifier separation performance. So if you have knowledge or data or literature values to say, look, I'm going to a higher efficiency cyclone, or I'm adding more water at the cyclone feed, I'm going to get a selectivity index improvement, now you can model it and see what that's worth to you in your circuit, whereas before there was not really a guideline for that. So at this point, we've completed step 3. We've modeled our target CSE improvement. We found the D50C and water balance we need to achieve that condition in the plant. In step 4, on the next video, we'll need to calculate what changes we need to make at the pumps and cyclones to get this new water balance and cut size. So for now, you can see that Streamline allows you to model any and all CSE improvements, reliably estimate the circuit benefit, however you choose to take it. In this case, we chose to take it through reduced energy. You'll see in your demos, your demo files, that there are some other scenarios, scenarios 2 and 3, that show essentially the same thing, CSE improvement, but either increasing tonnage or grinding finer, perhaps for better recovery. I hope you've enjoyed this video, and go ahead and you can proceed to video number 4, or the next video, step 4, to see how to do the actual cyclone sizing and pump sizing exercise. Thank you.